Hello everyone. In this video, I'll be presenting a few important results from this paper titled Further Optimal Regret Bounds for Thompson Sampling. This was authored by Shipra Agrawal and Naveen Goyal, and it was published in AI Stats in 2013. So, yeah, moving into the setting. As we considered the same setting, this is the same setting from the previous two videos. So we have n arms with bounded rewards. So here we consider it to be within 0 and 1. In fact, we only consider it to be 0 and 1, since we are considering only one of the algorithms presented in this paper. So yeah, and arm I reward comes from this Bernoulli distribution with parameter mu I, which is the mean of the arm. So yeah, and the pulls are all IID, and the usual assumptions we make are every arm has distinct rewards, and yeah, mu1 is the optimal reward. Yeah, now moving into the algorithm, we begin with setting a prior distribution pi1 as the product distribution of with beta distribution with parameters 1 and 1. This is nothing but a uniform distribution between 0 and 1. So yeah, now at each time t, the algorithm does these 4 steps: 1, 2, and 3, and 4. First, it samples from the pi t distribution. So for t equal to 1, we already have a prior here, this one, and yeah, we'll be updating in the 4th step. Yeah, we play an arm I of t, which is this largest sample from here, from the set. So that is mathematically written in this way. Yeah, after choosing this arm, when we play this arm, we get this reward RT, which is nothing but the Bernoulli distribution with this parameter mu subscript I of t. In the next step, we finally did the posterior using base rule. Yeah, so pi t plus 1 is equal to the prior times the likelihood. In fact, since RT, the reward, only takes 0 or 1, we can comprehensively write a few of these steps in this way. Let's see. So the prior, when we start this one, right, we can assume setting parameters called Si and Fi to be 0, and we can take pi1 to be product of I is equal to 1 through n beta of Si plus 1 comma Fi plus 1. So similarly, during the updation of the posterior step, we have to just check these two values. When R of RT, when the reward is 1, we just update the corresponding arms parameter S. We just add 1 to it, and similarly when the reward is 0, we update the parameter F. So, and likewise, pi t plus 1 is nothing but the product of these beta distributions. So yeah, we'll move on to some definitions here. So the reward defined as RT it's just the expectation of these sums. So that is the difference between the maximum reward minus the reward which the algorithm chooses at time t. So we just add all these differences from time 1 through capital T. So previously we saw that we could write it in this form where ki of t plus 1 is the count of arms I being selected from time 1 through t minus 1. So yeah, this is ki of t, and delta I is nothing but the difference between the max reward minus the I times reward. Yeah, we define the k divergence. Yeah, since we are having Bernoulli distribution, we get the simple expression, two terms in a summation form. Yeah, and then we move on to describing the main result. Yeah, I mean, this is one of the results in this paper, but there is another algorithm which is being presented in the paper, which I won't be discussing in this video. But a lot of the proof ideas which I'll be presenting now for this current algorithm with beta priors can be applied to the second algorithm in the paper as well. So if you are interested to see more details about that second algorithm, you can refer the paper. So yeah, the main result is says that for any finite t and any epsilon, fixed epsilon, between 0 and 1, not 0, the regret of this Thompson sampling algorithm with beta priors is bounded has some constants here, but grows with log t, and the number of arms comes into the picture in the constant part. So yeah, in the one of the previous videos I presented a lower bound for this problem. I'll give a link to that video in this description below. So what that says is that was a result from Lai and Robbins paper. So we have the lower bound R of t, sorry, Lai and Robbins. It's actually say in limit RT over log t is lower bounded by the constant delta I by mu I. So considering this lower bound, this algorithm is tight compared to UCB algorithm which I presented earlier. So yeah, that is one comment. But yeah, there are some algorithms which actually make UCB also tighter. It's called the KL UCB. Maybe I'll whenever I make the video I can provide the link in the description box below. Yeah, let's continue on proving this result. Yeah, first let's have some bigger picture of the proof. This is a very simple description. Let's see. We actually wait for the suboptimal arm I to be played enough times so that it concentrates in this fashion. So this step is where we get the logarithmic regret. So we need at least that is the um, philosophical idea. So we need some amount of samples, some minimum amount of samples, so that we can guarantee that this suboptimal arm, I mean, you can identify the suboptimal arm. Yeah, so that is the idea. And then in the second idea is that we start with uniform prior. So let's say at some step the arm one's posterior is like this, with which is having very high variance. So this is the probability of uh, theta 1 of t falling below mu I. So when this happens, we'll be picking up this suboptimal arm I. So we want to analyze the regret when this happens. So this is a bigger picture idea. I'll make it more clearer in the proof. So now for the proof sketch. I say this is a sketch because few of the constants are really hard to present in this video, so I'll be skipping those finer details. But yeah, I would be giving bigger picture ideas wherever needed. So yeah, let's continue. So now we limit our analysis to just the one of the terms in the regret, expectation of ki of t plus 1. So if we show this, then the regret is I mean, the main result can be shown. So yeah, just a minute. Yeah, I think there is no delta I here. So yeah, this is what. Yeah. So I can just quickly say why this is enough. So this implies RT, which is this expectation. Sorry, it's a summation of these things, right? So yeah. So let's see. Summation of I is not equal to 1 delta I times the expectation of ki of t plus 1. So now this is upper bounded by this term here. So log t by t times 1 plus epsilon square plus O of n by epsilon square, because we are summing over I. So yeah, this was the main result which I had written earlier. So yeah, so that is why this is enough to show this part. So now moving on to the details. For any epsilon between 0 and 1, but not 0, one can choose xi such that it lies between mu I and mu 1. Yeah, the picture makes it clearer, I guess. we can choose xi between mu I and mu1 such that the distance between xi and mu1 holds this part, and then we can as well choose yi, which depends on xi and epsilon in this fashion, such that the distance between xi and yi satisfies this equation. So this follows from analysis and Archimedean property. So yeah. So now moving on to the more details. So we define some events here. So yeah, we have 0 and 1, mu and mu1, and we have xi and yi as defined earlier. So now we define this event ei mu of t such that the average samples, the mu I hat of t, the empirical average, stays below xi, and then we define another event here, ei of theta, ei theta of t, where the sampled value from the arm I at time t is less than this yi value. So these are the two events which we'll be using to split up the regret term. So let's go ahead. So now we have this regret term which we are focusing on. So this is nothing but the summation. So I mean, this just follows from expectation of an indicator of an event A is nothing but probability of A. So that is why this follows. Now yeah, we further split these into some mutually exclusive events in this fashion. So first, ei mu of t, a complement, and then the other version is these two events. So these are like mutually exclusive events. So yeah, some interpretation here. So yeah, we'll be bounding each of these terms separately. So what is our aim? Our aim is to show that this term is bounded by a constant. So this is because we'll show that this term is bounded by the probability of playing arm 1. Hence eventually we'll try to show that it is actually bounded by a constant as well. Second term, we actually say from this figure, let me redraw that. So this is 0, this is mu I, this is mu1 and 1. So what this is saying is, and this is xi, xyi. So we are currently in the event e mu I and ei theta complement in this part. So it says okay, and one more thing, let's say after some time around the suboptimal arm, the distribution is like this. So we hope that after some samples, the probability of selecting arm I and the sample theta I of t falling after yi. So this area is low. So and that is why we expect after sufficient exploration of this suboptimal arm I, that is with these many samples, that is log t over the distance between mu I and mu1, we expect this term to be bounded by this up to some constants. So the third term, yeah, as well, we just use the Chernoff idea. Some concentration inequalities like Chernoff idea to bound this by this epsilon constant. So yeah, so that is why the second term is the one which is contributing to the log t part, and the other terms are the constant terms. So the second summation, yeah, is the exploration part, where you are exploring, you are actually sampling I forcefully up to these many samples, just to get the confidence of that you are actually sampling suboptimal arms. So yeah, so now we'll go into the details of these three summations separately. So we'll first define I mean, this is a hand wavy definition, but for the detailed definition you can look at the paper. So this script ft, you can think of it as some history or which collects the arms which are played and the rewards observed until the time t. So and we define this the small lowercase letter pi of pit as the probability that the arm I sampled crosses is greater than yi given the history up to time t minus 1. So now towards proving the bound for the summation of represented by this one, we present lemma 1, which is the same lemma in the paper as well, so that I've matched these numbers so that you could look at the papers same as in the paper. So yeah, for all time t from 1 through capital T and an suboptimal arm, yeah, we have this result. So probability of sampling this suboptimal arm can be upper bounded by the optimal arm with this inequality. So further we can observe that given the history up to time t minus 1, we know mu hat of t, which is the empirical average, so hence we know ei mu of t as well. So that is why we can remove this these events here. Yeah, so that is why these two are equivalent. So now we'll just prove this part. So yeah, a short proof for this is yeah. So firstly, we can just write p of a given ab given c as p of a given c times p of b given ac. So yeah, that is why we are just considering this part here, because this is the same on both RHS and LHS. This gets cancelled. So yeah, first consider the LHS here. So given this event, yeah, we can say that selecting the suboptimal arm I implies that all the other theta j's are less than yi. So that is why this inequality is coming from the monotonicity property of the probability. And then we just split these events here. Yeah, for the sample theta 1 you don't need any information regarding the other events ei, so that's why you could remove that event. I mean, because independence kicks in. So and then this term is nothing but 1 minus pit, which is written here. So we can assume this as some constant c1, a non-zero constant. That is this is non-zero because yi is strictly greater than 0, and hence this probability is non-zero. Yeah, I mean, it is as well strictly greater than 0. So yeah, so now consider the RHS term. So like the previous setting, given this event ei or theta and the history, the event which says that theta 1 is greater than yi and other theta j's are less than yi actually implies that we are picking arm 1. So that is why we have the other side inequality here. So yeah, if we follow the previous steps here, we get pit and the constant c1 as well. So when you divide a by b, we'll get the result from lemma 1. So yeah, so the lemma 1 and lemma 2 actually implies that the summation of 1 is bounded by a constant. Yeah, as I have written here, lemma 2 is just the, I mean, it's just a cumbersome to present in this video. Yeah, all it does is it carefully analyzes all the binomial sums and things like that to finally conclude that it is actually bounded by a constant. So yeah, but I'll give some insight here, like what can happen. Let's see, we have the summation of represented by this number 1. So from the tower property of the expectation, we could write it in this way, and then this the expectation inside is nothing but the probability of this event from lemma 1. This is by lemma 1. We can upper bound this term by the optimal arm selection. So here the expectation is over theta I, which is coming from this posterior distribution pi t. Yeah. Yeah, this is the term which is too numerical to analyze and too numerical to come around to present in this video. So yeah, I can just post some ideas here how this is actually bounded by some constant. So yeah, as I've already written here, So we have this plus events, so E and EI theta, EI mu and EI theta, and we are picking the arm 1. So after like arm 1 is played many times, we can assume that the distribution is small enough around mu1 so that it concentrates. So yeah, that is why we could say that this term here, the numerator is actually represented by this part, the area where the probability is calculated, the left to yi, and the denominator is the probability which comes right of yi. So as you can see, as in arm the optimal arm is sampled many times. The numerator divided by the denominator, it actually keeps reducing exponentially. So could assume this is how we can assume that it's actually bounded. So yeah, that is why I have written the summation is bounded by some constant. And this is because eventually arm1 is played exponentially many times, and the area of yellow divided by the pink area is so low after time t0, or some sufficiently large time. So now we'll move on to the second summation term. So here we have this term here. I'm just repeating. So so now here we have these two events. EI mu and EI theta, the complement, and we are sampling the suboptimal arm I. So the hope is that after many samples, the distribution concentrates around mu I, and the after mu I, and as you can see, this probability can be upper bounded by the probability of EI of theta t complement, which is this area, the yellow area here depicted. So the hope is that these many samples are enough. That is log t many samples, some up to some constants, are enough, is what the claim is. So let's go into the details of the proof. So we have lemma 4, which says this summation 2 is bounded by log t divided by the scalar divergence between xi and yi plus 1. And we already saw that this relation from the assumption of epsilon. So so we have to just prove this part. So a short proof again for this lemma here. So we again start with the summation represented by this 2. We directly assume there is some li which we'll design later and yeah, we split this summation into two parts. You could upper bound the first summation here by KIL of Li, since the probability here can be upper bounded by probability of IT equal to I. So because probability of A given B is less than probability of A, and probability of A comma B, A intersection B is less than probability of A. So using these properties and the definition of Ki of Li, you can actually upper bound by this term. So the second summation, yeah, you could actually use the previously mentioned ideas where given this event, yeah, we are just removing this event here, so that is why it is an upper bound. So now so we can actually write this is equal. So yeah, I'm just forgetting the conditioning event here, so I'll just fix that. So conditioned on mu I hat of t is less than xi. So yeah, so yeah, this part, it's actually given the history, we know mu hat, and then we will know the posterior distribution from which the sample is coming from. So that is why we can replace this with the beta distribution. So since the posterior is nothing but the beta distribution with some parameters expressed here, you could replace this summation by this one. So yeah, you can notice that this is actually the complementary CDF of the beta distribution, so which can be upper bounded by this term. So this is just coming from the concentration bound. So yeah, so now we actually know that this mu I hat of t is less than xi, so this further bounds, the distance between xi and mu I further bounds this term. So yeah, finally we get this part. Now we actually select what Li is. So suppose this Li is the largest time step until this Ki of t is less than this log t over the distance. So this can be, this actually comes directly from this term. So you want this term to be constant, which is independent of the capital T. So now if we choose Ki of t in this way, we can further bound the summation by this. And yeah, here the summation we could just further upper bound by t equal to 1 through t instead of just Li plus 1 through t. And now this is nothing but 1 over t, and the summation is just equal to 1. So yeah, this is the end of the second summation. So now we'll move on to the last third summation. So the third summation has just one event in it. So yeah, firstly we can define a new variable which we'll introduce in this summation, so which is called v0, vk. So we will set v0 as 0 and vk as the kth time the arm I has been played. So yeah, that is what this variable vk is representing. So we can upper bound this summation by this expectation. So firstly you can just rewrite this expression as expectation of the indicator function, and then you can split it into this sums of vk's. So here this is an upper bound because vk might not cover the entire time index, so that is why this inequality is coming from. So now we further analyze this term. So firstly, within these time instances, we know that ei of mu of t isn't changing because mu I hat is fixed. We are not sampling the arm I from vk plus 1 through vk plus 1 here in this summation. So that is why we are fixing this event. And now the variable t is only in this event, this part. So that is why we can take this event outside like this. So now as I said, we are sampling this arm I only once in this time in between these time indexes. So that is why this value is 1 here. So now we all know again from the previous fact that from the Chernoff bound that this is true. And this is just the from calculus, and then this is just the integration bound, and then from Pinska's inequality we know that the KL divergence is actually and the L2 distance is related in this fashion. So and we have already assumed that xi and mu I have a distance, so we can actually show that xi minus mu I is greater than some constant times the epsilon. So that is why we have this expression. So it's the constant terms. This constant is the problem dependent constants where mu i's and delta i's comes into picture. So for more details you could look at the paper, but it's not necessary. So now we just combine all these three summations which we have shown earlier. So the first term is bounded by constant, the third term is also bounded by constant, the second term which contributes to the log regret is coming from the exploration cost. So we are exploring different suboptimal arms so that we are confident enough to eliminate those arms from consideration. So the hardest part in this proof was to prove the bounded regrets, especially this part. So where we showed so here, right, in this part So the idea is simple, but the analysis and I mean the details of the analysis takes a few nuances to be taken care. So yeah, I think that is the end of this video. Let me just add one more point here. mm, yeah I think I already mentioned that this actually complements the result from Ryan Robbins 85. So mm, yeah, this paper is a classical paper because this is the first paper which proves that Thompson sampling actually achieves this lower bound. So there are many Thompson sampling algorithms which have made its debut later. So yeah, I could present some of the interesting parts later. So look forward to presenting, and hopefully you will be interested as well. So yeah, thank you.